So this is indeed about some experiment, but first let me address the question that's in everyone's minds, which is, when is the next conference? And just so you know, like we're organizing TQC this year, it will be in Portugal, and there's still some free places, and also we're looking for sponsors. So several research groups have already sponsored the conference, and if you'd like to, please talk to me. Good, so this is indeed about thought experiments and trying to implement them in a quantum computer, or at least as a quantum program. And it's trying to work with Nuria, Simon, and Renato. And whatever I'll say, it's not only a paper on the archive, but there's also all the code on GitHub, and you can go there and try to play with it. And what we did here was try to make up kind of a full suite, like a mini software package where you can go and program your own thought experiment, and you fit in what's the protocol of the experiment, what are like all the rules of logic that people are allowed to use, what interpretation of quantum theory you want to plug in, and then it tells you if some paradox emerges. And I'll explain what I mean by this, okay? So as an analogy, who knows Maxwell's demon thought experiment? I imagine most people know of it. So the idea is that Maxwell thought at some point, so what if there was a little demon standing in a box with gas, and he let all the slow particles go to the left, and all the fast particles go to the right. This can be done at no cost by just opening a gate selectively, and then you end up with like a colder gas on one side and a hotter gas on the other side, and you could just, now let the hot gas expand, and this looks like you're getting work out of nothing, right? And the solution for this was, of course, that, this was one thought experiment that tested that there was something wrong with the theory of thermodynamics, right? Either the laws of thermodynamics are wrong, or there's something we're not considering, we're not modeling physically, right? Which was precisely the case in this case, right? And yes, and when you try to think of an experiment within a theory, it's very hard sometimes to understand what are all the hidden assumptions that go there. And by trying to code this into software, we try to make this a little bit more explicit. Okay? So in the case of Maxwell's demon, the solution was, of course, that, well, you're not modeling the brain or the memory register of this demon, and if you did, you knew that the process of acquiring information, you need to store this information somewhere, and if you want to use this in a cyclic manner, then at some point you need to erase this information, and this costs work, right? And this led to the whole field of the work cost of processing information, why do computers dissipate heat, and so on, right? So, and it all started from this very naive thought experiment that no one was thinking about actually implementing at the time, right? I tell you this because I'll talk about measuring quantum agents, right? Okay, so let me just prime you with what I think the anatomy of any physical theory is that there is some part of the world that we describe as physical systems, like I'll describe these things as quantum, for example, but there's also something that we necessarily need to leave out and just think of as abstract. So for example, when I make a measurement and then I see an outcome, and then I do all this processing of the outcome, even at the end of a quantum circuit, all this processing is now, I now have this classical outcome. And by classical, we mean kind of abstract. We're not modeling physically, right? And then there's like what happens at this boundary between what's abstract and what's physical, right? So here lie things like the state, the dynamics, and so on, and there lie things like all the post-processing of information, and logic, and probability theory, and so on, right? And here, what lies is like, what happens when a measurement is implemented, right? What happens physically to the things? What is like the measurement update rule, and so on. All right, so, and there's different types of boundaries that we put on theories. So this one is a critical case, right? Where we saw like the theory is just not consistent if we only model this kind of systems as physical, and we leave like the agent's memory as abstract. But if we model everything as physical and think of the thermodynamic cost of everything, then it works, right? But there's also other cases where we have to do it for practical reasons, right? Like even solving the hydrogen atom or very simple atoms. If you were to model the whole thing as quantum, this is a horrible calculation. Whereas if we just model like these things here as an abstract potential, right, and the only quantum systems we're thinking of are the electrons, then we can actually reach some conclusions. We do this in all the physics, right? We are always doing approximations and cutting corners, and it's a matter of seeing, did this cause any big problem or not, right? Okay, and just to make sure we're on the same page, the same is true of quantum measurements, right? We know that everything that's going on is a physical interaction, and unless you believe in some very exotic variations of quantum mechanics, then even in the Stern-Gerlach experiment, when the photon hits the screen, then this is also some physical interaction. Eventually, some photons will hit my eyes, and this information will be processed in the brain, and all this thing is a giant unitary, unless you believe that quantum mechanics breaks down at these scales of like human beings, right? Right, but for all sorts of practical reasons, we put a cut somewhere, and this is the Heisenberg cut, right? And I'll say this now because a big criticism of everything that I'll say, a very popular criticism, is that, well, of course, if we treat like the whole world as quantum, then we never see a paradox, we just see this unitary evolution. And like, yes, but that's not the question. For practical use, in order to be able to use a theory to make predictions, we need to put this cut somewhere, right? And then the question is, what are the consequences or what are the limits of doing this? And in Wigner's friend experiment here called, so Wigner is Ursula, this is precisely what happens. So you have an observer in the box, this is Alice, she measures a quantum spin, and she models just the spin as quantum and herself as an abstract thing, right? So she thinks of her outcome as classical, but Ursula can, of course, model her as fully quantum, right? So here on the left, what we have is like the choice, how Alice represents her measurement, and it can be just like a measurement with an outcome, or she can even think that, well, part of my memory actually gets entangled with the qubit, but at some point I need to make some projection here, and I have this post-measurement state, right? Whereas Ursula can, or Wigner if you want, can model the whole thing as a unitary interaction, just like in the Stern-Gerlach experiment, right? The Stern-Gerlach experiment is like the spin degree of freedom gets entangled with position, and here it's exactly the same, right? Is it okay so far? Good, so this experiment, I'll just tell you very briefly the setting. It's about 4 agents that all have different choices of boundary, meaning that they choose to model each other as quantum or abstract based on personal preference, right? So Alice will model the whole of Bob's lab and the spin he measures and the spin she measures as a quantum system, whereas Bob will just model the 2 spins as quantum, and then Ursula will model this 2 as quantum, and Wigner will model this 2 as quantum. But the point, for a spoiler of this thing, is that they will reach a series of individual statements about all the outcomes that they get, which, when put together, lead to a contradiction, right? So what will happen in this experiment that we'll get into later, so this is the Frauchiger-Renner experiment, for those who don't know, is that Wigner will measure something, and whenever he sees that he gets some outcome that we call okay, and that Ursula also got okay, he concludes that Ursula knew, that Bob knew, that Alice knew that he would actually get fail. And this tells us what? It tells us that, well, it's like you try to make one of these logical puzzles with people wearing hats of different colors and trying to guess their own hat color, but you reach a contradiction, right? So if this happened to you, you'd say, well, someone is lying in this setting, or the logic system I'm using is not right. And here there's many ways to formalize this theorem. The original one is not the best, but the way I like to think about it these days is that, well, if you think of a practical physical theory, meaning this, that we always select something as physical and something as abstract, and we want agents to be able to place this boundary wherever they want, to move this boundary. We want the physical domain to be quantum, to be explained by quantum mechanics. And then we want that each agent can apply like subjective, like classical logic. And in particular, you want to be able to combine statements of different agents, then this theorem says that this is not possible to combine, which should be problematic because, I mean, this is, again, a very abstract thing of measuring quantum agents and sounds completely far off, but you could think of something more practical, like having a little network of quantum computers, and you want them to be all coherent, to process all the information quantumly, and you never measure them, and you want to see if you can like trust chains of information across this network. Yeah. Good. So why did we decide to write this as a program? Because there's so much, since Renato and Daniela's paper was out, there's been so much controversy in the foundations community that at some point we just decided, well, we need to force people to kind of use one framework to make their assumptions very explicit. And this allows us to also then, if someone comes up with, oh, I have a new interpretation of quantum theory that does not lead to a paradox, then we can like very quickly try out a different experimental protocol and see if that theory still works then. And in general it doesn't, right? This is a big open question, like you can't evade this theorem without making your theory trivial. Okay, so how much time do I have at this point? Enough? Okay. I'm sorry. Okay, so then let me just see what let's just see what I mean by reasoning. So let's first just think of very simple experiments. So Alice has a qubit. It doesn't matter for now which state it is. It's that. It's the qubit R. She measures it. And if she gets outcome 0, she prepares a second qubit S in state 0. If she gets it outcome 1, she prepares it in state plus. She gives it to Bob, and Bob also measures it in the 0-1 basis, so the Z basis, right? And the game is just Bob needs to guess what Alice's outcome was based on this thing, right? So there's 4 possible inferences, and only one of them is true, right? So if his outcome is 0, what can he conclude? Does anyone know? So if he measures this, he measures a state, he knows that the state was 0 plus, and he obtains outcome 0. Then, I mean, if he only does this once, he doesn't know anything, right? It could have been either state. But if he gets outcome 1, well, he could never have gotten that outcome with, is this a laser pointer? Light. Ah, right. You could never have gotten outcome 1 if it was this state. So if he gets B equals 1, he knows that Alice prepared this state, so he knows that she must have gotten A equals 1. Is that clear? So, like, concludes that, well, this is the only true inference. And now, how do we formalize this reasoning of his? Well, one way to reach this is for Bob to run a little simulation of the experiment. So he needs to think of Alice as classical because he needs to think of, or abstract, as I say, because he needs to think of her outcomes as classical real things. So he models the whole thing, right? He says, well, this is Alice's measurement. Then we project in her memory, we get some outcome. And then what she did is preparing 0 if it's 0, or preparing a plus if it's 1. It's a gate, it's a controlled Hadamard if we're looking from the outside. And then I entangle myself with it. I measured. Now we project in my memory, we see B. We have here the outcome A. And now we just look at correlations in this thing, right? So this is one way to simulate Alice's experiment. And then he concludes, okay, this is the only right inference. Okay? And now we want to model not just this, but we want to model now Bob's brain working during the experiment. So imagine that he did this before, right? He did all this thinking before, saying, well, if I see 0, I can't conclude anything. If I see 1, I know I know I can conclude this thing. And now we want them to actually run the experiment. Okay, sorry. And we want to model his brain, right? So we saw this kind of, now we're looking from the outside, so we're not projecting, we're looking from the perspective of a third agent who is all on the outside and everything is unitary. But now after Bob getting his outcome, his brain does some reasoning, and our brains are also quantum systems, right? So we can model this somehow. And this looks complicated, but it's actually very simple. So it's just a circuit that says, it says the following: if my outcome was 0, and I had this inference saying that if B equals 0, then A equals 0, then update this thing. It's just like a logical circuit that just combines what my belief was, which is encoded here. It's saying, oh, like we saw before, only this inference is true, all the others are false. And then it just combines, it says what's in the outcome, combines it with the inference, and then updates the prediction. Yeah? So we're not modeling like a very intelligent quantum agent, we're modeling like a machine, right? Like if you had programmed a machine to play tic-tac-toe, and this would be like, oh, see what my adversary played, see what the next step is in this case, then do the next step. And now if you look at this from the outside, so now we start having, the experimentalists in the audience getting a bit nervous, given the quantity of qubits that is coming out of here. So here are Alice's actions, here are all of Bob's actions, so his measurement, then his brain update. And then how do we check that Bob was right or not? Well, we can just measure here at the end what Alice's outcome was, what Bob's predictions were, and then check for correlations, right? And that is one step of the experiment. And then the experiment builds up, and I'll just give you maybe one more step so you see how these things come across and why it's fun. So the idea is that now we have this agent Ursula. She sits outside Alice's lab, and she's going to measure all of Alice's lab, meaning that maybe we have one qubit register for simplicity that has Alice's outcome and the spin that she measured. She thinks of Bob as classical because she wants to think about, depending on my outcome, what did Bob measure? And Ursula measures in a special basis. That's just the Bell basis here, and there's only 2 possible outcomes because of the correlations. So, and this is the circuit from Ursula's perspective, right? Of course, everyone has a different circuit because they all model different things differently. So first we had, well, Alice did her measurement, she's quantum, so I'm not projecting on anything. Then Alice did this conditional preparation. Then maybe Alice did some reasoning, but we're giving Ursula the ability to undo all of Alice's reasoning. Her reasoning will come later, what it was. And then she just performs this Bell measurement here. And she knows that in the meantime, Bob came here and he also measured Alice. And now we do project because we model Bob as classical, right? And then she just wants to find correlations between these 2 things. So what does she need to think about? So again, here are the 3 agents. This is going to be her conclusion. And why? Because she just needs to think about, well, what was the state, the quantum state at this point? And the quantum state at this point has that horrible form. But the only thing that matters is that the only state that has overlap with OK on what Ursula measured is Bob having measured 1. Okay, so if you go through the maths and so on, she can see that Ursula concludes that if she gets OK, then it meant that Bob got 1. And then she can think, well, and if Bob got 1, what we saw before, then we know that Alice got 1 as well. Right. And then the next step is just Wigner doing the same here. Oh, sorry. The next step is Alice thinking about this. So Wigner is going to come here. He's going to measure Bob again in this same Bell basis. And now Alice, here in the past, is going to make a simulation of this experiment, modeling Bob as quantum, and thinking about the outcomes that Wigner got. And she runs exactly the same circuit, but it's a bit different because she models herself as classic, so at some point here she projects, then the Hadamard, then Bob's measurement, then Bob's reasoning, then Wigner undoing Bob's reasoning and doing this measurement. And then she just needs to think about the overlap between her outcomes, or correlations between her outcomes and Wigner's outcomes, right? And what she concludes is that, well, whenever I get a 1 here, so I prepare state plus, after all of these things, what happens here is that the state here is actually a bell pair, which is precisely this fail outcome. Okay? And this leads us to A equals 1 implies his outcome is fail. And now the only step that you're missing here is that, I don't know if I have this. Right. Up. Right. Is that Wigner also models these two labs as quantum, so all of these labs as quantum, he models the whole thing, and he knows that there is some probability that's not 0, that both of them get okay, right? But now he knows that if he gets okay, and Ursula gets okay, then I know that Ursula knows, that Bob knows, that Alice knows that I'll get fail. Right? That's kind of the paradox. And what's nice about this, the program is that it allows us to model all of this. So where did interpretations of quantum mechanics come in? So if all these agents were working under a collapse theory, we believe in objective collapse of the wave function, or we believe that collapse happens at this scale, then all of them would have the projection after each agent's modeling, and then we don't have a contradiction, right? If they all believe in, I don't know, cubism, then they're not allowed to combine statements from each other. If they're Bohmians, they have harder problems. Then they have, yeah. Okay, and the nice thing about this thing is that it's kind of all very modular, so you can go in and try to code what an interpretation of quantum theory is, and that's just modeled on what can I conclude from seeing an outcome about what's going on in the rest of the experiment, what are your consistency among agents rule, like this kind of just combining inferences, how do you model a quantum agent, how do you model their brains, how do you model their measurements, and again, all the whole experimental protocol, so you can go and try. And just to finish, some people have thought about, well, can we just weaken this assumption? So one is well, let's just say we're not allowed to combine knowledge or make any kind of predictions if I know that one of the agents will be measured later, which avoids a contradiction here, yep. But it really breaks down in very simple scenarios, and we can come up with very, very simple experiments where if you want to restrict logic, then you cannot make any useful predictions in Bell scenarios even. And if you want to justify this, say, oh, there's some physical reason why you want to justify this thing, then we also can come up with a different experiment that shows that, well, then you believe in supraluminal signaling. And then what does it mean that someone will be measured? Because, our brains are always interacting with the environment. We will all decay and die, and all of these things, can be modeled as quantum maps, and quantum maps can be seen as measurements. So what is your class of measurements that are problematic? That is very unclear. So another very popular defense is, well, if agents keep track of the context of every statement, what was the exact experimental setting, what were they considering quantum or not, where did all this information come from, then we don't reach a paradox, because at some point there'll be some incompatibility in context. And it's nice, but then you're just restating the problem, and you still have not told me what's the condition for compatibility. And also that's not how we do physics, right? The whole point of quantum computing is to take very complicated physical systems and make them model, oh, here are your 2 qubits, so that the theorists don't need to think about the whole superconducting hardware that's going there, and only need to model it as different things, right? So if we were forced to do this to keep our logical integrity, then our memory would scale very, very bad. And if you believe in many worlds, which is okay, maybe there's no problem in concluding that I got some outcome okay, but I also but someone else concluded I would get fail because everything happens at once. Fine, but then what you do with this theory, what you do with a theory where, with a world where everything happens, what's the predictive, what kind of predictions can you make? How do we apply this in everyday use? So it's very unclear. Yes, and that's it. Thank you for your attention. You're now free.
Okay, thanks a lot for this talk. Are there questions? Yes. Okay.
Hi, thank you, that was great. Have you read any of Howard Wiseman's work in this space? Is there any sort of compatibility with that in your experimental setup?
Yes, in fact, we have a grant proposal in the works to try to actually adapt this software to treat these things. And we still have not reached an agreement into whether their assumptions are compatible with ours. I think theirs are a bit stronger because one of their assumptions is that kind of events are universal, and this, I don't see why this would be a natural thing to assume. Because, you know, an event is just some physical evolution. Nature is moving, doesn't care what you consider an outcome or not, or an experiment or not, right? This is a subjective choice. Whereas we only need that, you know, agents have a subjective notion of events, and there's some compatibility conditions. So I think our assumptions are a bit weaker, but there's no clear way yet to map onto each other, and we want to work on this.
Okay, cool. Thank you.
So was there another question? Because I think if this is not the case, because I guess everyone is eager to get some coffee before the bus ride, but I think there's a lot of possibilities to chat further. So thank you, Lydia, and all the speakers for today, for the wonderful talks, and I think there were some last announcements.